Hello. So today we're going to look at limit review number 1, which officially begins our review for the AP test. So let's consider some function y equals f of x, and the statement, the limit as x goes to a of f of x, or we could say the limit as x goes to a of y. Both of these creatures here mean the same thing. And if they indeed equal L, where L is a real number, we say this limit exists. So what does the limit do? The limit asks what the y value gets close to. What does this y value get close to as x approaches some x value? It is most important to note that for this limit to exist, L, this guy right here, must be a real number. Or we say the limit does not exist. So let's start off here with an example of a graphical limit. And we have some limits down below. This is the graph here of y equals f of x. I have right here, we're talking about the domain from -6 to 4. And the first question is, the limit as x goes to -4 of y on this. So what you're asking yourself, as x approaches -4, and as x approaches -4 from the left and from the right, what does the y value approach? Well, the y value approaches from the top and the bottom 2. So we say this limit is 2. Same as if I look at example B here, the limit as x goes to -2 of y. What would that be? Well, now I'm going to approach, let me get these guys out of here. Now I'm going to approach -2. I'm going to go from -2 from the left and -2 from the right, and I'm going to investigate what the y values approach. Well, the y values approach 1. So this limit is 1. And the final example I have on this graph, or another example I have of this graph, is this limit right here. As x approaches 1 of y, what would that limit be? Well, let's approach 1 from the left. Ooh, and if I approach 1 from the left, it looks like the y values approach 3. But as I approach 1 from the right, it looks like the y values approach 2. Therefore, there's no way that this limit could exist. And we'll talk more importantly about that later on. So this limit, we're going to say, does not exist. It doesn't exist because the limit from the left does not equal the limit from the right. I'm going to add one more example on this graph. If I put an open circle here at this value 3, and I just extend my graph of f of x to go on, and I ask this question. What is the limit as x goes to 4? We can see of y or f, it doesn't matter. We can see that this limit does not exist either, since the limit from the left does not equal the limit from the right. So we look here, as x goes to 4, the y values go to 1. As x goes to 4 from the right, the y values go to 3. I'm going to do one more example with this graph. I'm going to come up here with my eraser, and I'm going to put an open circle here at 6. I'm going to connect my graph. And then I'm going to put a solid circle up here. And I'm going to ask the very important question. What is the limit as x approaches 6 of y? Well, let's investigate that. Let's get some of these marks out of here. Okay. So now, let's approach 6 from the left and 6 from the right. And here is where the real definition of a limit would come into play. Because what I want to worry about is what the y values get close to, not what the y value is. So if I approach x, if I approach 6 from the left, what does my y value approach? Well, here's my y values. They're approaching, it looks like 1. And as I am approaching 6 from the right, what are my y values approaching? Again, the y values are approaching this guy here, 1. By the definition of a limit, then, this limit is equal to 1. And we want to note here that this does not equal the function value at 6. So this is an open circle. Make sure that you know that this is an open circle. I'm going to redefine that a little bit clearer. So the function is defined at 6, but this solid circle is the function at 6. This point right here is 6, 2. So f of 6 is equal to 2, and 1 does not equal 2. So this is very important. This graphical concept of a limit, as x goes from the left, from the right, what do the y values approach? Let's continue with this page. Oh, and here we have new notation for this left-hand and right-hand limit. This last limit, which they mean this limit right here, whoopsie, this limit here, which does not exist, it does not exist because this creature here, which we call the right-hand limit, does not equal the left-hand limit. And it's hard to see here. This, the notation here, is the limit as x goes to a, and I have a little plus sign of y. That little plus sign means that I'm approaching a from the right. This is the right-hand limit. This is how we denote a specific limit as x approaches a from the left. So this particular notation for right-hand limit and left-hand limit is going to be very important. And we saw in our graph multiple examples of left-hand, right-hand limit. Here the left-hand limit it did indeed equal, the left-hand limit did indeed equal the right-hand limit right here. And we saw where the left-hand limit did not equal the right-hand limit. And that limit does not exist. And that's the one we were talking about here. As is the limit as x approaches 4 from the left and right does not exist either. Okay, let's go to the next page and see what we got on the next page. So just more examples for left-hand, right-hand limit. So very good. So let's take a moment and I will remind everyone that at any time you can pause this video. Let's go from -4 to the left of my function f of x. It doesn't matter if I put y or f of x in for that. This means I'm going to approach -4 from the left, and I'm going to compare that to this limit as x approaches -4 from the right of f of x. And I'm going to make sure that I say, hey, this is the graph of y is equal to f of x. So let's look at those two specific right-hand, left-hand limits. And this, it's hard for me when I create this graph to create open circles. That's going to be an open circle there. And this is going to be an open circle there. So I would ask you to pause the video just for a moment and see if you can come up with these limits, what these limits are. And you are correct. As x approaches -4 from the left, What does y approach? Well, it looks like y is approaching -1. And as I approach -4 from the right, what does y approach? These y values are approaching 3. And what I would say, it's important to note then that the limit as x approaches -4 of f of x does not, if I can spell not correctly, does not exist. Okay? And we can see from our graph that there is another limit that does not exist, and that's this limit right here. We can go the limit as x approaches 1 of f of x does not exist. Okay, so those were a couple of nice examples of right hands and left hand limits, limits that did not exist, and limits that did indeed exist. Okay? All righty, let's see what's next on the docket. Looks like we're going to talk about this deal of vertical asymptote. So let's come up here and delete some stuff so that I have some room to talk about vertical asymptotes. And what I'm going to do here is I'm going to extend the graph of f of x, and I'm going to create a vertical asymptote here at 6. Let's see here. I think I can do a line. I think I can do a dotted line. I think I can. And I think I can move that line over to be really nice. I can't. And so now I'm going to take my graph. I'm going to go down. I'm going to go up here this way. And this line right here at x equals 6, we know x equals 6 from previous discussions in pre-calculus and calculus that we're going to call this a vertical asymptote. Just abbreviate that bad boy right here. Well, what happens to the limit here? What does happen to the limit as x approaches 6? If I'm approaching 6 from the left, where does the limit go? Where do the y values go? Well, what happened to the y values is the y values are going to decrease infinitely large, i.e., the limit as x approaches 6 from the left of f of x is equal to -infinity. Keep in mind, this limit does not exist. Infinity is not a real number. But we say specifically this limit goes to -infinity. It's unlike where the left-hand limit does not equal the right-hand limit up here prior to our prior examples. This thing actually goes to -infinity. And if I look at this guy right here, as x approaches 6 from the right, where does the y values go? The y values increase infinitely large, and we would say this right here. The limit as x approaches 6 from the right of f of x, that bad boy goes to +infinity. And what does that tell me? This is by definition a vertical asymptote. So let's look at the definition of a vertical asymptote, and here it is. So when the y values go to infinity, the limit does indeed not exist, and this is the definition of a vertical asymptote. And here's the formal definition of a vertical asymptote. The limit as x goes to f of x. If it goes to positive or negative infinity, then x equals a is defined to be a vertical asymptote of the graph y equals f of x. So here's a little analytical limit. Let's see what this is. Let's take the limit as x goes to 2 of this function right here, 1 over x minus 2. Well, that limit, if I were to do that analytically, I would get 1 over 0, which does not exist. But really the best way to do this limit is use our pre-calculus skills, and let's graph this bad boy. And we know right away from our pre-calculus discussions that this rational function does not exist at 2. It explodes at 2. It has a y-intercept. If I put x equals 0 into that bad boy, I'm going to get y is equal to negative 1/2 right there. That graph does not cross the x-axis, so it's going to have to do this. It's going to explode down. And if I look at a value greater than 2, this guy right here is x equals 2. If I look at any of these values here, the function is going to be positive. In fact, if x is 3, it's going to be 1. So the graph, I should have probably sketched that in red so I don't get confused with the actual graph. These guys are all going to be positive. And that leads us, again, to the definition of a vertical asymptote. Sorry about the little interference here. So therefore, this limit, and we could be specific about this, the limit is x goes to 2 from the left of this guy right here, 1 over x minus 2. That guy right there goes to negative infinity. This limit, the limit is x goes to 2 from the right of f of x, 1 over x minus 2. That goes to positive infinity. Therefore, x equals 2 is a vertical asymptote. Just abbreviating right there for us. Asymptote. Okay, vertical asymptote. And we can also call these vertical asymptotes V dot A for standing for vertical asymptote. Let's do a little page extender right there. Vertical asymptote, x equals 2. Keep in mind, the limit could just go to infinity. But good enough for examples. Well, let's do one more example. Find the vertical asymptotes of this guy right here. Let's go this function, which is equal to 1 over x squared. Well, I could do the graphical representation of that first. Let's do. Well, I know x squared is always going to be positive. So the graph of that, we will graph this rascal in red. At 0, this thing is undefined. This guy here, this graph looks like this. And we say x equals 0 is a vertical asymptote. Why? Because the limit as x goes to 0 of f of x is equal to positive infinity. So x equals 0 is a vertical asymptote because the limit of f of x as x goes to 0 goes to positive infinity. Because as x approaches 0 from both right and left, the limit does indeed go to infinity. And we notice the right-hand limit goes to positive infinity, and the left-hand limit goes to positive infinity. But infinity is not a real number, so that limit does not exist. There's some confusion about that. That limit does not exist if it goes to infinity from the both. The limit, for a limit to exist, it has to equal L. Our discussion was about vertical asymptotes. Okay, let's continue on here. Next page. And we're going to be, many times, we're going to be asked to find a limit analytically. And I'm going to tell you right now, boys and girls, friends and neighbors, this is easy. Simply do a direct substitution. Simply directly substitute the x value into the function. If you get a real number, then by golly, that is the limit. So let's try these examples here. These are limits analytically is what we're doing here. So all we're going to do, we're not going to graph this and do this graph, although we could, but we don't need to. So all we're going to do is put 2 in wherever we see x. So this is going to be 3 times 2 squared minus 5 times 2 minus 2. And let's see here. This is going to be 3 times 4, which is 12, minus 10, minus 2. That limit, by golly, is going to equal 0. And as always, check my arithmetic. I think the arithmetic is correct there. 3 times 2 squared is 4. 3 times 2 squared is 12. 5 times 2 is 10. It's minus 10 minus 2. That, I believe, is correct. Let's do this guy right here. Let's go to a different color. Jump down here. The limit as x goes to -1 is going to be -1 squared plus -1. -1 squared, oh my goodness gracious, is 1 plus -1 is equal to 0. And I can trust me that all analytical limits do not equal 0. It's just that I picked two, just so happens that I picked two limits that went to 0. So let's do this last limit here, direct substitution. I'm going to directly substitute, and this is going to be 7 times the sine of heavens to Betsy, pi over 6. Well, I know that the sine of pi over 6 is a real number, and so 7 times a real number is a real number. Let's figure out what the sine of pi over 6 is. And if I look here at the unit circle, going back to some long time ago, this guy right here is going to be your pi over 6. That angle right there, this is the unit circle. That point right there is going to be square root of 3 over 2, 1/2. And therefore, the sine of pi over 6 is 1/2. And this is going to be 7 times 1/2, which is 7/2. Very good. Let's continue on here. I think I'm going to pause the video here. I'm getting about 20 minutes. I don't want to go over 20 minutes for any one video. So I'm going to continue with the limit laws on the next video. All right.